A laser operates based on the principle of stimulated emission of radiation, a quantum mechanical process first theorized by Albert Einstein. The term laser stands for light amplification by stimulated emission of radiation. To produce laser light, energy is first pumped into a lasing medium, which could be a gas like helium-neon, solid like ruby or Nd, Yg, liquid dye, or semiconductor. This energy input excites atoms or molecules, promoting electrons to higher energy levels. Under normal conditions, most electrons occupy lower energy states. However, lasers require a population inversion, a state where more electrons exist in excited states than in lower energy levels. Once this inversion is achieved, an incoming photon of a specific energy can interact with an excited electron. Rather than being absorbed, the photon causes the electron to fall back to a lower energy state and emit a second photon that is identical in energy, phase, polarization, and direction. This is the essence of stimulated emission. These identical photons travel back and forth within an optical cavity, usually formed by two mirrors, one fully reflective and the other partially reflective. This setup amplifies the light through repeated stimulation, producing a beam of coherent, monochromatic, and highly directional light. When the light intensity builds up sufficiently, it escapes through the partially reflective mirror as a laser beam. Laser light exhibits several defining characteristics: coherence. All photons are in phase with one another. Monochromaticity, light of a single wavelength or color. Directionality, the beam remains narrow over long distances. High intensity, concentrated energy in a small area. In Star Wars, the lightsaber is a fictional weapon often imagined as a concentrated beam of energy. While real lasers cannot stop midair or clash like swords, lightsabers share conceptual similarities: a focused, high-energy, and highly directional light source. This imaginative comparison helps illustrate the extreme power and precision of real-world laser systems. Ultimately, lasers are a brilliant fusion of quantum physics, physical chemistry, and engineering. They underpin a vast array of technologies, from medical devices and telecommunications to industrial cutting tools and scientific research, showcasing the profound utility of controlled light.